Hi guys, today I'll be explaining the chemistry quiz of term 1 week 6. So let's start. Which of the following factors increase the rate of a chemical reaction between a solid and an aqueous solution? A solid and aqueous, these are the keywords. Remember, solid, liquid, aqueous. What affects them? We have the temperature, we have the surface area, you have the addition of a catalyst, and you have what? The concentration. Now notice we left out what? We left out the gases. What about the gases? Gases, all of these affect them in addition to volume plus pressure. So remember, anytime you see solid, liquid, aqueous, you know that it's temperature, surface area, catalyst, and concentration. These are the things that affect the rate of a chemical reaction. However, anytime you see gases, it is the temperature, surface area, catalyst, concentration, in addition to what? The volume and the pressure. These are very important, okay? So looking back here, we have a solid and an aqueous solution. So what are the things that affect a solid and aqueous solution, as we said before? We said the concentration, the temperature, and the surface area and the addition of a catalyst affect solid and aqueous. We know if you increase temperature or concentration or surface area or more of a catalyst, then definitely the rate will increase. So remember, solid and aqueous. On liquid, if you increase the concentration, if you add the catalyst, if you increase the surface area, and if you increase the temperature, these all will increase the rate of the solid and aqueous and the liquid. However, for the gas, it is all including the volume and the pressure. Question number 2. When will it reach equilibrium? Here is our equilibrium sign. There are two ways to define equilibrium. You can either reach equilibrium, and how do we know we reached equilibrium? When no more observable changes, meaning macroscopic. I'm just gonna write macro for now, okay? Or if the forward rate is equal to the reverse rate, okay? So this is if we reached equilibrium. However, if we need to recognize, this is very important, to recognize equilibrium, how do we recognize it? It is recognized by a constancy of macroscopic properties in a closed system at a constant temperature. Now, all of these are words, they might be confusing, so let me break it down. When we reach equilibrium, we can see no more changes, okay, in the properties that are visible, such as the macroscopic properties are observable or measurable properties, such as the pressure, the concentration, the color, the size, the volume. All of these that are observable, that you can see, okay? These are called macroscopic properties. If you cannot see them, if you don't see any changes in them, that means you reached equilibrium. Or if the forward rate of reaction is equal to the reverse rate, then you know, خلاص, you reached equilibrium. This is to reach. How about recognizing? You recognize equilibrium when you see that the macroscopic properties are constant. What does it mean? That means it doesn't mean they are equal. It means that if you have, for example, 2 atmospheric pressure here and 3 atmospheric pressure here, no matter what you do, it will stay 2 here and it will stay 3 here, no matter what you do. So this is a constancy of macroscopic properties in a closed system, very important, and at a constant temperature. Now, when will it reach equilibrium? They don't need us to recognize, they need us to reach equilibrium. It is when the forward rate is equal to the reverse reaction rate, or when changes are no longer observed. That's it for number 2. Question number 3. Which of the following are true about macroscopic properties? We said, what about macroscopic properties? They are visible without visual aid, meaning you don't need a microscope, you don't need any tools to help you see them. Visual aid or visual assistance, okay? They are seen and measured. Okay, this is wrong, they are not fixed properties. Okay, they are not fixed properties. So pretty much this is it about equilibrium. Based on what we said, which of the following are true about macroscopic properties? We said macroscopic properties, they do not need visual assistance, so you don't need the microscope to see them. Then they are measured or seen properties like pressure, color, or concentration. And they change, and pretty much these are the two ones for macroscopic properties. Now, what can be concluded from the equation? We have an equation of equilibrium. Okay. What about the equation of equilibrium? We said when we have equilibrium, then the forward is equal to the reverse. Okay, that means they can take place at the same time. Another word for at the same time is simultaneously. Okay. Another thing about equilibrium is that the reactants and the products are always present, meaning that if you have this or this, no matter, like if you have N2O4 or 2NO2, no matter what you're gonna do, you're always gonna have N2O4 and always gonna have 2NO2. Okay, and definitely it goes either N2O4 gives us 2NO2 or 2NO2 will give us N2O4. If this is the case, then for every one molecule of N2O4 consumed, 2 molecules of NO2 are produced. Or for every 2 molecules of NO2 consumed, 1 molecule of N2O4 is produced, like this. So, what can be concluded from the equation? We said the forward and the reverse reaction may take place simultaneously. They are constant, that's why they take place simultaneously at the same time. Since they're happening at the same time, the forward and the backward, okay? The forward meaning from reactants to products, and the backward meaning from products to reactants, okay? They happen at the same time, so they are constant, and that's why they are simultaneously. Since they happen at the same time, we're always gonna have N2O4 molecules and NO2 molecules, because they're both happening at the same time. You're gonna have always N2O4 and always N2O2 existing at the same time. Then 2 molecules of NO2 are consumed for every 1 molecule of N2O4 formed, or 1 molecule of N2O4 is consumed for every 2 molecules of NO2 formed. That's pretty much it for number 5. Now, equilibrium. Some facts about equilibrium. At equilibrium, the reactions proceed spontaneously or directly, so that they can reach equilibrium directly. Okay? Another thing, equilibrium favors the greatest randomness and the least energy. So let me write them. We have the reactions occur spontaneously or directly. Spontaneously. Alright? Then we have it favors greatest randomness and lowest or least energy. Okay. Also, as the temperature decreases, it favors the one with less heat, and as here this is temperature, and as the temperature increases, it will favor, let me not do like this, as the temperature increases, it will favor the one with more heat. Okay, so which of the following are correct about equilibrium? And based on the notes that we just wrote, okay, we know that equilibrium tends to favor the state of greatest randomness, not lowest randomness. Also, at very low temperatures, equilibrium favors the one with the less heat, with the less heat. Then equilibrium, it takes the least energy and the most randomness, so the greatest randomness and the least energy. And finally, we said that the reactions, they proceed spontaneously, directly to approach the equilibrium state. So, question number 6. When is equilibrium reached? We said equilibrium is reached when macroscopic are constant. Okay? And when the pressure is constant, because pressure is what? It's a macroscopic property. And another thing, equilibrium is reached when no changes are detected. So that means, when is equilibrium reached? It's when the macroscopic properties become constant, when the pressure is constant, and we can detect no more evidence of change. Okay, so equilibrium is reached when everything is constant and there's no change. However, equilibrium is recognized when there is a constancy in the macroscopic properties. Number 7, which of the following is considered a macroscopic property? We said macroscopic properties are visual. You can see them, they're visible. So we have concentration, it is visible, it can be measured. We have pressure, it can be measured and it's visible, it's visual. And we have atomic number. Atomic number, it's not visible. You need a microscope to see exactly and to measure. The color is very visible, very visual. And then finally, the mass number, you also need a microscope to see it. So think of the ones that you can measure without using a microscope. You don't need a microscope to see concentration. You don't need a microscope to see pressure, and you don't need a microscope to see color. The only things you need a microscope are the atomic number and the mass number. Question number 8. Le Chatelier's principle states that. What is his principle? He says, we have a system. If a change happens to this system, for example, let's say we increase the concentration, it will partially counteract. Okay? What does this mean? That means you have reactants, it gives you products, or the products gives you reactants. Let's say you increased the concentration of the product, so you're increasing the concentration of the system. What will happen? It will partially counteract. So the product will do the opposite of what we did as a change. So to keep this equilibrium, to keep this balance, okay, it will do the opposite of what we did as a change. So if we increase the concentration, it's gonna decrease the concentration. And what happens to the reactants, to the other side? It will follow the change that we did. So it will follow the increase in concentration. Again, let's take now, if we're gonna do a change from the reactants to the products. If we're gonna, let me think. If we're gonna decrease the concentration of reactants, okay, or we're gonna decrease the concentration of the system, consequently, it will be mainly in the reactants. What will happen? The reactants will say, okay, let me do the opposite. So if the reactants do the opposite, it will increase in concentration. And so then, what will follow the change that we put? The other side, which is the product. So the concentration of the product will decrease. That means when a system is at equilibrium, it is subjected to a change, the system will partially counteract the imposed change. Counteract means it will do the opposite. Question number 9. Which of the following sealed flasks indicate a saturated vapor at equilibrium? What do we mean by saturated? Let's take these, for example. Let me draw one because sorry for the bad drawing. Okay, we have this conical flask. We have this liquid over here, and here we have the evaporated molecules. At some point, at any point, we don't know which point, the liquid going to a gas will be equal to the gas going to the liquid. So then this is saturated. And if you notice, this sign is very familiar to what? To equilibrium sign. So that means a saturated liquid. Let me draw it again. A saturated liquid. This time it's green liquid. Okay. A saturated liquid is when the liquid evaporating to a gas is the same as the gas condensing to a liquid. And so it is also at equilibrium. So definitely just even without thinking like this, see which one has the equilibrium sign, choose it. That means it's saturated. And because it's at equilibrium, just choose the one with the equilibrium sign. Question number 10. This is from way before. If you decrease the temperature of a reaction, the reaction rate will decrease and the number of effective collisions will decrease. However, if you increase the temperature, the reaction rate will increase and the effective collisions will increase. Question number 11. Okay, in this graph, just look at this graph. We have A, this is the heat of reactants. Then we have C, this is the heat of products. Then look very carefully. We have B, it's the activated complex. And then what happens? We have X, it is delta H or the enthalpy change. And finally, we have what? Y, which is the forward reaction. How do we know it's a forward reaction? Because it's a reaction occurring from the reactants to the products, where the reactants is losing heat to the product. So if the reactants has, no, it's not losing heat to the products. The reactants has more heat, so R has more heat than products. What does this say? If the reactants has more heat than the product, if you remember from previously, then this is exothermic. Okay? So, we said that the potential energy or the energy of the reactants was A, then the energy of the products was C, then the activated complex was B, and then the activation energy was Y, the activation energy of the forward reaction was Y, and then the enthalpy change of the reaction was X, the enthalpy change or delta H. Now they're telling us they added a catalyst. What does the catalyst do? The catalyst will keep the reactants here, it will keep the products here, but what will it change? It will change the pathway of the activated complex. So what happens? The Y will become smaller and X stays the same. That means X is not changed. So X we said is delta H, or X is not changed, and then the activation energy, okay, or the energy of the complex is faster. It becomes faster, but in the graph it decreases. So because it is faster, it will take less time, so then the slope or the curve will decrease, so it will decrease then. Now, upon the addition of a catalyst, the value of X, we said it will remain constant, while the value of Y will decrease. And we said because the products is lower than the reactants in this equation, it is not this equation, this graph, then it is exothermic. Question number 12. Question number 12. In 3 different experiments, equal masses of excess calcium carbonate were reacted with the same volume of hydrochloric acid. In each experiment, one factor affecting the rate was changed. The volume of carbon dioxide released was measured every 5 seconds. So, they're telling us if we have a lower temperature, if we decrease the temperature, if we play with the temperature, it will only affect the slope. So see which two have the same plateau. This is the plateau, and this is the slope. So definitely A and B share a plateau. That means they're not. So again, since A and B share the same plateau, and there's only a difference in the slope, that means there isn't a change in the concentration. Whenever we're talking about the change in concentration of an acid, both the slope and the plateau are affected. Now, if we're ever talking about the surface area, so using lumps rather than powdered, okay, the surface area will only affect the slope. And finally, the addition of a catalyst will only affect the slope. So the only thing that affects both the slope and the plateau are the concentration of the acid, or in this case, it's the limiting. Usually it's the limiting, but in this case, it's the acid. Okay? So, if we have a lower temperature, then we choose the one with the steepest slope, which is B, or the lower slope, which is B. Now, a lower concentration of hydrochloric acid, we said that hydrochloric acid is what? The limiting. How do we know? Because we have excess calcium carbonate. So since it is the limiting, and we have a lower concentration of the limiting, then it has a slope and plateau lowered. So which one has a lower slope and a lower plateau? It is C. Now, using lumps rather than powdered calcium carbonate. So they're saying they're using lumps rather than the powder. So definitely this will cause an increase. So if he's using lumps, it will cause a decrease because the surface area is becoming less. So using lumps rather than powdered calcium carbonate, which is gonna cause a decrease in the slope because we have a less surface area. Now finally, the addition of a catalyst is the most obvious one. It will increase the slope, okay, but it won't affect the plateau. So again, a temperature will affect the slope. The concentration of limiting, keep this in mind, the concentration of limiting will affect the slope plus plateau. Okay, the addition of a catalyst will only affect the slope. So please keep this in mind. Also, I forgot this one, using lumps rather than powdered calcium carbonate will only affect the slope. Now, question number 13. Based on the collision theory, a decrease in the concentration of a reactant. So if you're decreasing the reactant, then you're going to decrease the reaction rate. Why? Because you're decreasing the number of collisions between the particles. However, if you increase the concentration, then you will increase the reaction rate because the number of collisions between the particles will increase. Question number 14. This is very, very important. So, let me draw a graph, okay? Or let me use a different color, black, because I need the red. Why? Okay. We have the forward reaction, and then we have the backward reaction. So this is the forward, and this is the, let me take blue. This is the backward or reverse reaction. Now, before the equilibrium happens, we need to reach equilibrium, okay? So before we need to reach equilibrium, this is what our graph will look like. So to reach equilibrium, what do? We need to decrease or lower the rate of the forward reaction, and we need to increase or higher the rate of the backward or reverse reaction. So it's all logical. Keep this graph in front of you. This is normal, not equilibrium. Okay? This is the forward curve and this is the backward curve. So to reach equilibrium, we need to decrease the forward curve or decrease the rate, and we need to the rate of the forward curve, and we need to increase the rate of the backward curve. So here it is decreases and here it is increases. Now, at equilibrium, the rate of forward reaction and the rate, okay. So now what happens? This is the same graph, okay? And we reached equilibrium. So this is the forward, and this is the backward, no, and this is the backward. So let me do it better. There we go. No, it's still bad, oh my goodness. Okay, here we go. So this is the forward, and this is the backward, or the reverse, however you like to name it. Okay, so at equilibrium, what happened? We decreased the rate of forward and we increased the rate of backward. Now what happens? They are equal. The forward and the backward are on the same line. They have the same y and the same x, so that makes them equal. And since they are equal, then the concentrations, or not the concentrations, everything in general will become constant. That means at equilibrium, the rate of the forward reaction and the rate of the reverse reaction are equal, okay? And everything, including the concentration, the pressure, and whatnot, becomes constant. Now, the chemical equilibrium is referred to as dynamic. Why do we say something is dynamic? It's because the microscopic reactions, they occur at the same time. Okay, they occur. So for example, you have reactants gives products and products give reactants. This occurs what? At the same time. So you'll have reactants giving products and products giving reactants at the same time. This is what we call a dynamic, because it exists two opposing, the reaction and the product. They are opposing processes, but they continue to occur simultaneously, or they take place simultaneously, which means at the same time. Okay, but you do not see any visible macroscopic changes. So no visible macroscopic changes. So chemical equilibrium is referred to as dynamic due to the existing of two opposing microscopic. We said the reactants and the product are opposing, but they happen at the same time. They continue to take place simultaneously at the same rate because the forward reaction and the backward or reverse reaction are equal, and you don't see any macroscopic changes. What does this indicate? As we drew in the graph above, if you remember in the red and blue, this is our forward rate, this is our reverse rate, they meet at the same, and so here is where the equilibrium starts. Don't take this because it doesn't continue, and the reverse has to be bottom, not up. And this is wrong because they do not reach equilibrium, and here they depart from equilibrium. So take this one. Why? Because at equilibrium it will continue. Here, like here, this one down, it reaches equilibrium, but then they split, so it doesn't stay in equilibrium. We need it to stay in equilibrium. Question number 15. Very, very important question. Choose the correct answers to fill in the blanks. Okay, whenever we have a question like this, we have 4 steps. 4 steps. The very first step is find the change. We call this the imposed change, or IC. The second step is according to Le Chatelier, or to Le Chatelier's principle. Okay, we need to state his principle. The third step, okay, is why this happens, or this happens by, and finally the fourth and last step we have as a result. Now keep these in mind while we solve this question. Choose the correct answers to fill in the blank, predicting the effect of the given changes on the equilibrium and the amount of SO2Cl2 produced. Okay, when Cl2 is removed, okay, keep this in mind. This is the first step, the imposed change, which is Cl2 is removed. If Cl2 is removed, will we have a bigger concentration or a smaller concentration? Of course, we will have a smaller or a less concentration. So definitely the imposed change is that Cl2 is removed and its concentration decreased. Second step, okay, we have Le Chatelier's principle. What does this principle state? It states that a change that happens to a system at equilibrium will be partially counteracted. Okay, so how do we partially counteract in this case? So this happens by, if the concentration decreased, so let's write it. We have this one, yes? We decreased the concentration of this one. So to counteract it, it's stubborn. This Cl2, it's stubborn. It said, I want to do the opposite of what you're telling me to do. So the concentration instead will increase. So this happens by increasing the concentration of Cl2. Okay? Now we increase the concentration of Cl2. What happens? As a result, since we increased the concentration of Cl2, okay, we need to decrease the concentration of something. So we increased the concentration of Cl2, so we'll go to the opposite side, which is the product side, and we have SO2Cl2. It will now take the weight of decreasing its concentration. So as a result, SO2Cl2, the concentration will decrease. Okay, so when Cl2 is removed, okay, So again, when Cl2 is removed, the equilibrium position shifts backward and the concentration of SO2 Cl2 decreases. So let's take it like this. Okay, we increase the concentration of Cl2. Cl2 is stubborn. We decrease the concentration of Cl2. So Cl2 is stubborn and it said, I don't want to decrease, I want to increase. So now it will increase in concentration. So what will happen? As a result of the stubbornness of Cl2, the other side of the reaction, which is SO2Cl2, will get affected. So instead of the Cl2 concentration decreasing, okay, instead the SO2Cl2 concentration will decrease. Now, let's take it like this. If the counter action increases, that means it moves the equilibrium position backward. However, if the counteraction decreases, then it moves the equilibrium, okay, it doesn't fit here, the equilibrium position forward. Okay, so let's re-explain it since we have this rule in mind. We have Cl2, we are removing Cl2, so the concentration is decreasing, but Cl2 will counteract. How will it counteract? It will do the opposite of what we gave it as a command, so it will increase. So now the counteraction is increasing, okay, that means it will move backward, okay? So the equilibrium position is backward, okay? And so now, since the concentration of Cl2 increased instead of decreasing, we go to the other side of the reaction, which is the products SO2Cl2. It will do then the decreasing for the Cl2. Now, when SO2 is added, so now we are increasing the reaction of the concentration of SO2. SO2 wants to counteract, so to counteract, it will decrease in concentration. And we said anytime we decrease, okay, the equilibrium, I'm gonna call it equilibrium P, the equilibrium position will move forward, okay? Now, since it decreased, we will go to the other side of the reaction, which is the SO2Cl2, and it will take the command that we give it, that we gave to this one. It will say, okay, I want to do the increasing. Since SO2 does not want, I will do it. So now the SO2Cl2 will increase. So when SO2 is added, the equilibrium position shifts forward, and then the concentration of SO2Cl2 increases. Question number 16. Very, very important. Okay, we have Le Chatelier's principle. They're telling us if the pressure is increased by decreasing the volume. Whenever we're playing with pressure, we have to know that pressure only affects gas. So if you have a solid, cross it out. So the only solid in this whole equation is the C solid. Now, we have reactants and we have products. Yes? Now we have to count the number of gases in the reactants and the number of gases in the products. So here we have one gas and here we have one gas. Since they are equal amounts of gas, there is no change. Now, here we have 2 gases and we have then 3 gases. So if we have 2 gases and 3 gases, definitely if we put pressure, then the pressure of the 3 gases will move to the 2 gases. So for moving from the products to the reactants, this is what? A backward reaction. Okay, so it will shift backward. Now, here we have 3 gases and here we have 2 gases. Definitely the 3 gases will give pressure to the 2 gases, so we're moving from the reactants to the products. If we're moving from the reactants to the products, then it is a forward reaction. Okay? Now, finally, for this one, we have two gases will give us two gases. So there is no change since they are equal. So again, I will repeat. We have reactants in the gas and we have products. This is only in the case of gases. You remove anything, so remove non-gaseous. Over here we're gonna remove this. So now what do? You count the number of then you count number of gases in reactants and products. So let's say here there is 2 and here there is 5. Definitely the one with 5 gases will give to the 2 gases. So if we're going from products to reactants, then it is backward. However, if it was, for example, here is 7 and here is 3, the 7 will give to the 3. So if it's going from then the reactants to the products, it is forward. So here this is no change. This is shift backwards, this shifts forwards, and this is no change. Okay? No change is when you have the same amount of gases. Shift backwards is when the products will give to the reactants. Shift forward is when the reactants will give to the products. And again, no change is when they are equal amount of gases. Now, question number 17 is very, very important. They're telling us, choose the correct answers to predict the effect of changing temperature on the following chemical reactions using Le Chatelier's principle. So, remember the 4 steps we have to follow. First, we need to identify the change, so the imposed change. Let's take A as our example. Okay? A, we have the temperature is in the reactant side. Okay? So we're going to keep it in mind. We have, if the temperature is in the reactant side, then it is endothermic. Okay? Now they're telling us as the temperature decreases. So now we are decreasing the temperature. So the imposed change is decreasing the temperature of reactants. What will happen? According to Le Chatelier's principle, a counteraction will happen. So how will this counteraction happen? We say this happens by, if we're decreasing the temperature of reactants, a counteraction would be the opposite, which is increasing the temperature of reactants. Okay? After that, we have step 4, the final step, which is as a result. So since we increased the temperature of the reactants, heat. So for this increase in temperature to happen, what happens? The reactants will take heat from the products, so heat will be taken from products to reactants. Okay? So we are taking from the products to the reactants. Okay? Again, we are taking from the products to our reactants. As a result, the heat will be taken from the products to the reactants, and we have what? An increase, which is the counteraction. And we said anytime we have an increase as a counteraction, or if the products will give to the reactants, then the equilibrium position is backward. So, as the temperature decreases, the equilibrium position will shift backwards, and the concentration of SO3, we said the temperature will increase as a counteraction, so definitely the concentration of 2SO3 will increase. So, the concentration of SO3 increases. Now, this one is a case we have to really pay attention on. As the temperature increases, we have delta H is negative. So, if we have delta H as negative, that means it is in our products. So, equilibrium, sorry for the bad equilibrium, CO2 gas plus H2 gas plus the heat, which is 27.6. Anytime you have negative heat, you're gonna have to put it as positive in the products, okay? So if we increase the temperature, we are increasing this temperature. A counteraction will be what? A counteraction will be a decrease. So let's write it in 4 steps. Okay, let us write it in 4 steps. The first step is the imposed change. What's the imposed change? It is the increasing temperature. Okay, let me clear it out. The first step is imposed change. The imposed change is increasing the temperature of products. Now, what happens if you increase the temperature of products? We have second, Le Chatelier's principle, which states a counteraction. What happens as a counteraction or as a result? Okay, as a result of this counteraction, or this counteraction will happen by, first of all, if you're increasing the temperature of products, the counteraction will be the total opposite, which is decreasing the temperature of products. Now, the fourth is as a result. What happens if you need to get rid of the temperature here? How do you get rid? You will give it to the reactants. So as a result, heat will move from products to reactants. And we said anytime we are giving products to reactants, this is a backward equilibrium position. I'm not gonna write the full thing, okay? So as a result, you need to decrease the temperature of product. So how will you decrease the temperature? You will give it to the reactants, okay? As a result, the heat will move from the products to the reactants. And we said anytime we're moving from the products to the reactants, it is a backward equilibrium position. So as the temperature increases, the equilibrium position shifts backwards. And here we decrease the temperature, okay? If we decrease the temperature, then definitely the concentration in the products will decrease. So the concentration of CO2 decreases. Question number 18. Okay. Choose the correct answer to predict the effect of adding a catalyst. When you add a catalyst, it's not gonna change anything in equilibrium. It only it makes forward and reverse or backward faster. That's it. The catalyst will only make the forward and reverse or the backward faster. It will not change the concentration, it will not change the temperature, it won't change anything. So the equilibrium position will be reached faster. Here, will reach faster. Okay, whereas everything, which is concentration, temperature, pressure, volume, remains constant. Okay, so the equilibrium position is attained faster and the concentration of CO2 remains constant. Question number 19. Choose the correct answer to predict the effect of increasing the pressure by adding an inert gas on the following chemical reaction. Okay, this is very, look. We're adding an inert gas. What does an inert gas do? It doesn't react. Since it doesn't react, it has no effect. So the equilibrium position stays the same. It's not affected. And the concentration stays constant. So the equilibrium position is not affected, or it stays the same, and the concentration will remain constant. Number 20. This is very important. Remember from the previous question, excuse my bad drawing, okay, they said the liquid and the gas above the liquid is saturated. What does it mean? We have a liquid here and we have the gas here. That means the flow from liquid to gas, which is evaporation, and from gas to liquid, which is condensation, is equal. So the rate of evaporation is equal. So I'll write evaporation, this is evap, is equal to condensation. That means it is at equilibrium. So the rate is equal to the rate. Okay, so it is at equilibrium. Question number 21. Another important example. First, write imposed change. They said which of the following increases when the concentration of B decreases? We said concentration of B will decrease. This is our imposed change. Second thing, Le Chatelier's principle, a counteraction will occur. The third step is this happens by a counteraction will do the complete opposite of the imposed change, so it will increase the concentration of B. Okay? As a result, for the concentration of B to increase, this is step 4. Okay? The concentrations of C and D will decrease, whereas the concentration of A will increase. So think of it. If they are on the same side, okay, I will write it as a note. Same side equals same effect. Alright? So since A and B are on the same side and we increase the concentration of B as a counteraction, then consequently the concentration of A will increase. Question number 22. If the partial pressure of all gases is increased by decreasing the volume. Okay, we have pressure. Whenever we have pressure, we said we're going to take reactants and products. We're going to count how many gases in the reactants? 1. How many gases in the products? 2. So definitely if they are increasing the partial pressure, then 2 will give to 1, okay? The bigger number will give to the smaller number. So the products is giving to the reactants. This is a backward reaction. Okay. Now, definitely, since N2O4 is the reactants, its concentration will increase because the NO2 is given to it. And since the NO2 is giving to the N2O4, its concentration will decrease. It's very logical, this chapter. This chapter, chapter 1. Now, finally, we have more of the pressure. We have if the pressure of the system increased, we have 2 gases in the reactants. It will give us 3 gases in the products. So what's gonna happen? The product is gonna give to the reactants. Okay. So if it's gonna give to the reactants, then it's gonna be a backward shift, or it's gonna shift to which direction is the arrow pointing? I will draw it in pink. It's going from the product to the reactant, so it's going to the left. It's a left or a backward shift, okay? So since the product is giving to the reactants, then definitely the amount of products will decrease and the amount of reactants will increase. So if the pressure of the system is increased, the system will counteract by shifting to the left, okay? And the amount of O2, because they are the products, O2 and H2, they will decrease because the products are giving to the reactants. And finally, since the reactant is H2O, then H2O will increase. Let's submit and inshallah nothing is wrong. And thank God nothing is wrong. Thank you guys for watching. I hope you understood. Please, if there is a concept you didn't understand, let me know. I will be more than happy to explain it again.